Thank you all for joining us today.
Well, we'll get
My name is Matthew Walters, and for our Capstone project, we work with Hytrol Conveyor company who manufactures conveyors. And our goal for this project was to reduce their manufacturing scrap rate and their production costs. So we had the pleasure of working with two great industry partners from Hytrol, Felton Barlow, who is a manufacturing engineer, and Ken Nickerson, who is an industrial engineering manager. So we spent our first semester of this project analyzing Hytrol's manufacturing processes, which allowed us to discover that Hytrol has been transitioning the production of their parts from the laser cutter to the punch in an attempt to standardize their production. So this finding motivated us to create a cost-benefit analysis tool that will determine the benefits of switching the production of a part from the laser onto the punch. So this tool will provide Hytrol decision makers with the information they need to identify the parts that are best suited for the punch in order to have the most impact on reducing their scrap rate and production costs.
Now I'll go into a little more about Hytrol. Hytrol exclusively sells material handling equipment through their partners. They partner with many global customers through their Hytrol Integration Partner Network to help assist with projects of all shapes and sizes. These partners serve as the link between customers and Hytrol and form a system that can best be described as customers supplying demand, then the partners providing the design, which is given to Hytrol for production. The companies buy the equipment from Hytrol and then resell those products to Hytrol Integration Partner Network customers. The partners are responsible for design review meetings, engineering special items, product testing, and guaranteed shipment dates. Customers are able to use the interactive locator provided by Hytrol to be matched with a partner to fit the needs of their business. With customers including Fortune 500 companies such as UPS, Amazon, and FedEx, Hytrol has a large impact on the material handling market. As one of the largest conveyor manufacturers in the world, Hytrol produces a variety of products that includes acclimation, sortation, transport, pallet handling, and even in some cases the software that runs these products. There are two main categories of conveyors that they produce: gravity and powered conveyors. Gravity conveyors require no power to transport materials because they rely on gravity alone, and there are three different types: wheel, roller, and ball bearing conveyors. Powered conveyors, on the other hand, require power to move materials. There are 5 different types of powered conveyors: belt over, belt under, parcel, sorter, and chain driven. Parcel conveyors are Hytrol's highest demanded product, with the majority of sales being to Amazon. The effects of the COVID-19 pandemic on e-commerce have increased the demand for material handling products, which has led to an influx of business for Hytrol. Now Jasia will explain how raw materials are transferred through our system of interest and turned into the high-demand products that are crucial to the expansion and smooth operations of the material handling industry.
During production, orders typically follow the same process. Once Hytrol receives the order from the customer, they gather the raw material from material that's already in stocks or material that's ordered specifically for the customer. The raw materials are then sent to the brown or silver fabrication cell, depending on the type of conveyor demanded by the customer. So if the customer wants a belt over, belt under, sorter, chain, or gravity conveyor, it is sent to the brown fabrication cell. And if they want a parcel conveyor, then it's sent to the silver fabrication cell. The manufacturing processes that take place in the brown fabrication cell are laser cutting, punching, shearing, sawing, and pressing. And the manufacturing process that takes place in the silver fabrication cell is laser cutting. Once the order is being done manufactured in the brown or silver cell, it is then transferred to the designated color cell, depending on the conveyor, where further fabrication is done. And the fabrication processes that take place in the color cells are machining, brake forming, welding, and curve forming. And once it's done being fabricated, it is painted, assembled, and tested, and then sent to the customer. Our project focused primarily on the brown and silver cell, where the laser cutter and punchers are housed. And Cameron will now go into more detail about these processes.
Thank you, Jasia. So laser cutters use highly focused beams of light to cut through various materials. Multiple parts can be cut on a single steel sheet by laser nesting, and Hytrol's software that they specifically use for their laser nesting is called Radon. And Radon is nice because it accounts for the size of the steel sheet and the parts within the computer-aided design software, and it arranges these parts onto an operation in a feasible manner. This is then sent to the laser cutting machine. And the flexibility of the laser cutters really allow Hytrol to manufacture almost any custom designed part. However, Hytrol is concerned with a large amount of scrap produced from laser cutters. A punch forms a part by shearing metal between the upper tool and the lower tool. Lasers are responsible for skeleton scrap, and punches are responsible for black clips and slugs. Depending on the configuration of the punch and the die set, a part can be formed into almost any shape. Punching operations are optimized to reduce scrap, and the production rate is much faster than laser cutting. Because of this, Hytrol believes that they can reduce their scrap rate by manufacturing their high demand parts on punches rather than laser cutters. The skeleton, a byproduct of laser cutting, is the excess material left over after the laser cutting operation. On the opposite end of that are slugs, a byproduct of punching, which are the unused material that is punched out of the steel sheet, and black clips, which are the inverse of slugs, and they are the unused material that is not punched out of the steel sheet. Now, as we previously spoke to, Hytrol considers two main focal points when evaluating the manufacturing system's performance: process scrap and quality scrap. Quality scrap includes parts or assemblies that fail quality control. Process scrap is the byproduct of the machines that fabricate these parts, such as skeletons or black clips. This evaluation is done on a monthly basis and is derived from an equation involving cost of raw materials and pounds of raw materials purchased. This process can be shown by the gray image above, which illustrates the entirety of the Hytrol's raw materials produced for the month of January, in which Hytrol recorded $2.6 million worth of raw material and 4.2 million pounds of raw material. From here, Hytrol was tasked with locating the percent and cost of both the quality and process scrap. Now, as you can see, represented by the red color, a significant portion of the raw materials resulted in process scrap. Process scrap was responsible for 860,000 pounds of scrap and costed Hytrol $533,000. Additionally, process scrap was responsible for more than a fifth of the raw material, which can be multiplied by the cost of raw material to determine the total process scrap for the month of January. This information served us well by aiding our journey in narrowing down the area of focus to process scrap. However, it was still important that we investigate quality scrap to ensure that all measures had been properly accounted for. The pounds and percent of quality scrap, represented by the blue strip, is calculated to be 55,000 pounds of quality scrap and 1.3% quality scrap. From this, we noticed that the quality scrap was heavily disfavored in terms of scrap raw materials in comparison to process scrap. Additionally, quality scrap was significantly lower than process scrap costs. With all these parameters factored in, it was clear that the quality scrap lacked the sheer value in numbers to be considered the main area of focus. From the information above, we were able to determine the most likely area of focus, develop the parameters for our net present value equation, and focus on ways to improve the process scrap production time, as well as the percentage in process scrap in the brown and silver fabrication cells, simply by rearranging parts from a laser cutting machine to a punching machine. Now I'll turn it over to Christofel and let him discuss the performance of the system with more illustrative and graphic formats.
Thank you, Cameron. So these two graphs illustrate the system's current performance. The graph on the left visualizes Hytrol's monthly cost of purchasing raw materials. Since 2015, Hytrol has spent roughly $2 million a month purchasing raw materials. As these raw materials enter the manufacturing system, scrap is a common byproduct. This process scrap costs Hytrol on average $500,000 a month. This means that Hytrol only ends up using a little less than 75% of the raw materials that they purchase in a given month. This creates a serious opportunity for Hytrol to cut back on costs to save money for them and their customers. As Cameron spoke to earlier, scrap is produced at two main points in the manufacturing process, as either a byproduct of fabrication, that being considered process scrap, or by failing to meet standards during quality inspections, which is called quality scrap. As you can see in the figure on the right, process scrap contributes a much larger portion of overall scrap value, producing roughly 10 times more scrap than quality scrap. Although both types of scrap are important factors to understand, because of the sizable difference, we focused on the elimination of process scrap within our system of interest. To better understand where scrap was being produced within our system of interest, we conducted a root cause analysis. We met with two key stakeholders throughout this process that were able to give us a better overall understanding of scrap production within the system. We met with Cindy Liu, who is a quality engineer, and Chris Shepard, who is a quality assurance facilitator. We learned that Chris led a project in 2016 aimed at both tracking the cost due to scrap, as well as educating Hytrol's employees on scrap production on the fabrication floor. After meeting with them and reviewing the minutes from Chris Shepard's project in 2016, we were able to determine the main causes of scrap and assemble a fishbone diagram to break each cause down into components. This analysis found 6 main areas of issue, including human error, material coordination, quality control, engineering, and fabrication. So taking a look at the fishbone diagram, for example, under human error, which is found at the top left corner of the diagram, we identified that lack of training is a major contributor to human error. We also found that Hytrol faces a high turnover rate on the fabrication floor, which causes the continual need to hire new employees. As a result of this fishbone diagram, we concluded that the largest contributor to the scrap rate were punching and laser cutting operations, which is circled in red. This alone accounted for roughly 68% of the total scrap in 2019, which we determined from data Hytrol shared with us that summarized the scrap produced from each fabrication process from 2018 to 2020. Although a majority of this scrap is process scrap, which is unavoidable from fabrication, Hytrol believes that around 60% of the scrap produced from these processes could be minimized. Based on these insights, we then decided to focus on solutions that addressed laser cutting and punching. To determine the main contributors to process scrap, we conducted a Pareto analysis. After modeling, we uncovered a major shift in the main source of scrap from 2018 to 2020. In 2018, lasers, shown by the red bar, were the main source of scrap, producing nearly 8 million pounds of it within the system. In 2018, this accounted for about half of all scrap produced in our system of interest. If we compare these results to today's metrics, we see that the leading source of scrap production comes from punching machines, which is shown by the blue bar. Punching machines contributed to nearly 3 million pounds of scrap to date. The dramatic shift over the past few years poses a couple of questions, like why did we see this change and what created this shift? After talking with our industry partners, we found that this shift occurred because of Hytrol's conscious effort to reroute work away from laser cutting machines, which are historically more unpredictable in the amount of scrap they produce, to punches and die sets, where the scrap rate production is better understood. The shift from laser to punch also allowed Hytrol to utilize the many advantages punching machines have over laser cutting machines, which include lower production times, scrap rates, and operation costs. Next, I'll hand it over to Jasia, who's going to talk about how we use these insights to develop a mathematical approach to aid Hytrol in moving these parts from laser machines to punching machines.
To help us assist Hytrol in determining the benefits of transitioning parts from the laser to the punch, we created a cost-benefit analysis tool using net present value to evaluate the potential investments. This equation worked behind the scenes in our tool and is what helped us make our final recommendations. As we can see, there are 3 parameters included in this equation: the cost of the die set, the scrap cost savings, and the time cost savings. I will now go into more detail about each parameter. The cost of the die set is a huge component when determining the net present value of making the switch. Included in this parameter is the capital cost of obtaining the die set from either buying it from a third-party company or making it themselves. And they also have to include the monthly cost, the monthly maintenance cost of the die set, where we also have to include the time value of money using Hytrol's required rate of return. The next parameter is the scrap cost savings. Scrap cost savings is the amount of money saved if scrap produced on the punch is less than scrap produced on the laser. To calculate this, we take the pounds of scrap produced on the punch and subtract that from the pounds of scrap produced on the laser and multiply that by the cost per pound of raw materials to get the scrap savings for one part. We then have to multiply this by the utilization of that part to get the average monthly scrap savings for that part, where we also have to include the time value of money in this parameter as well. The last parameter is time cost savings. Time cost savings is the amount of money saved that corresponds to the amount of time saved that from switching production from the laser to the punch. To calculate this, we have to first calculate the cost to produce on each machine, where we take the cost per hour of operating on that machine and multiply that by the production time of operating on that machine. So we take the cost to produce on the punch and subtract that from the cost to produce on the laser and multiply that by the utilization of the part to get the average time cost savings, where we also have to include the time value of money in this as well. So once we have calculated all three parameters, that is the cost of the die set, the scrap cost savings, and the time cost savings, we add them all together to get the net present value of switching production from the laser to the punch. We are certain that this is a good way to calculate the net present value, but we are uncertain about some of the variables that go into the equation, such as the time to produce on the punch, because this is new. This will be a new production, and Hytrol doesn't have any times related to this to where we could kind of base our times off of this. So to help us with these uncertainties, we incorporated the Monte Carlo simulation into our tool. The Monte Carlo simulation for net present values allows for distributions to be assigned to these variables that we are a little uncertain about, and then it simulates a large number of iterations and calculates the net present value. In our tool, we decided to use 10,000 iterations. Matt will now go into more detail about how we incorporated this into our tool.
Awesome. Thank you, Jasia. So as Jasia mentioned, many of these parameters that go into our equation can be uncertain. So what a Monte Carlo simulation does is it pretty much allows us to attach a distribution to some of these uncertain parameters. And then it can calculate a distribution of net present value across many possible scenarios. So for example, take TL here on the left, which is the time to produce a part on the laser. And this is not exactly a constant value since it depends entirely on the nesting configuration of the parts. So therefore we can fit a triangular distribution to it using a lower bound, a most likely value, and an upper bound value. So our tool will also support for a constant and a uniform distribution as well. And so after all the parameters are assigned to distribution, we can then randomize these cost parameters across its assigned distribution, and then we can calculate net present value as many times as we want in order to get a distribution that is very similar to the one on the right here. So our tool uses 10,000 simulations, which means 10,000 different calculations of net present value. So it's recommended to use anywhere between 1,000 and 10,000, and the more simulations, the more accurate the results will be. And so with this distribution, we can do a couple of things. We can perform sensitivity analysis, find the confidence interval, and find the expected value. And so for our tool, we'll primarily be using this to find the expected value. And another thing we do is we find the probability of success. So this is essentially the percentage of net present value that is greater than or equal to 0. So in this example, with the distributions, every single one of the 10,000 net present value calculations were above 0, which means it was a good investment. And so this part would have a 100% probability of success. So this flowchart here depicts the logic of the equation that Jasia introduced and the Monte Carlo simulation, how these two are brought together within our cost-benefit analysis tool. So the first step, pictured in green here, is to enter all the cost parameters and all the distributions associated with them. These are all gathered from Hytrol subject matter experts, so they're assumed to be fairly accurate. And one thing to note is, in order to get good results with our tool, the data that goes into it must be fairly accurate. So like I mentioned, our tool supports for a constant, a uniform, and a triangular distribution for each parameter. So after this, the Monte Carlo simulation will begin, and it runs for 10,000 iterations. And so during each iteration, the cost parameters are first randomized across its assigned distribution, and then net present value, as well as rate of return on investment and payback period are calculated. So since this simulation runs for 10,000 iterations, once the simulation ends, we will then have 3 different distributions. We'll have one with 10,000 net present value calculations, another with 10,000 return on investment calculations, and the last one with 10,000 payback period calculations. So with these distributions, the tool will then calculate the expected net present value, the expected ROI, the expected payback period, and then it will use the distribution of net present value to find the probability of success. So all 4 of these values will be used to assist the Hytrol decision makers in identifying the parts that are best suited for the punch in order to have the most impact on reducing their production costs and their scrap rate.
Now I'm going to walk you through the decision support tool that we created for Hytrol. This tool is housed in Excel and uses the cost-benefit analysis equations that Jasia was speaking to, as well as the Monte Carlo simulation that Matt introduced to minimize, to find whether parts are feasible and objectively good candidates for punching versus laser cutting manufacturing. For this demonstration, we'll be using 5 of Hytrol's parts that are currently being produced by the laser cutting machines. We selected these 5 parts from a short list of 15 parts that Mr. Barlow, one of our industry partners, provided us data for. We selected our 5 candidate parts by considering their utilization, time to produce using a laser, amount of scrap per part on the laser cutting machine, and part simplicity or punchability. 4 of these parts have already been added to the tool and are listed in the list of parts list box that you can see on the screen. This demonstration will consist of adding the new part, checking and editing data for one of the already existing parts, and running the analysis that produces the metrics needed to compare the 5 parts that Matt just spoke to. To begin, in the workbook that houses this tool, we have 2 sheets, one for the welcome page, which is active and you are seeing now, and one for a database that holds all previously added parts, which is hidden. Because the nature of this tool is to compare parts that have already been identified as competitive parts for stock and punching, we will not be using it to compare more than 5 parts at one time. This means that realistically, there is not a large demand for mass data entry directly into the database. And while we could open up the tool to that possibility, we decided that in order to minimize user error, we would keep the database hidden and only allow user input through the features that we have provided. Speaking of the features, the first one I would like to show you is how to add a new part. The user will click on the Add Part button indicated by the red circle, and then this form will open up. When the Add Part form first opens, it's completely blank. The part name the user enters in the top left text box will be what is displayed in the list of parts on the welcome page and is the primary key for our database. The general parameters, Hytrol's rate of return, and the number of time periods will be used to further define and be applied to the calculations relating to the other parameters gathered by this form. according to our industry partner, Mr. Nickerson, Hytrol uses fairly standard values for these two parameters, those being the rate of return of 10% and a maximum acceptable payback period of 6 to 7 years, which we have associated with the number of time periods parameter. So moving on to show you what it looks like filled in, users have the ability to select the distribution checkbox next to each parameter, excluding the general parameters. By selecting the distribution checkbox, the user has the option to use a constant, uniform, or triangular distribution like Matt was speaking to before. The user simply fills out whatever data they have, and our code will decide whether or not the value entered corresponds with an average value or a triangular or uniform distribution. To save the data, the user will press the Enter Entry button, which will automatically error check the values entered for invalid entries such as non-numeric parameters, invalid distributions, and text boxes that have been left blank. If all is well, then the Add Part user form will close and take the user back to the welcome page. If there are errors, the user will be prompted to fix the errors found before they can be taken back to the welcome page. Seen here, indicated by the red circle, the new part has been successfully added to the list of parts. The next feature I would like to show you is how to edit existing parts. The user will select the desired part from the list of parts and then click the Edit Part button indicated by the red circle. This will open up the Edit Part form. And this form pulls all the previously entered data from the database associated with the current part. This allows Hytrol employees to update data that may have been entered incorrectly or delete a part that is no longer needed. Error checking is also accomplished by clicking both the Update Entry button and the Delete Entry button. And if all is well and valid, they will take the user back to the welcome page. The final feature I want to show you is the part comparison analysis. So to display this, the user can select up to 5 parts from the list of parts and then click the Run Analysis button. For this demonstration, we will be selecting all 5 of the parts. Then the metrics for the expected net present value, expected return on investment, expected payback period, and the probability of success are displayed for each of the parts selected. You can then press the Clear Results button to go back to the welcome page, or the Create Report button to generate a downloadable document. The Create Report button is indicated by the red circle on the screen. This report was requested by our industry partner, Mr. Nickerson, and contains the data points and metrics he would want to see if he was making decisions about the transfer of a part away from the laser cutting to the punching manufacturing. At the top of this report, there is a time and date stamp. The part name, description, material type, and utilization, which are all directly inputted from the user form, are included on this report. Also on this report are the calculated metrics that we just spoke to, which are expected NPV, ROI, payback period, and probability of success. This report can be saved and printed off to be used later by clicking the Save Report button that's at the top of this page. By creating this tool, we are standardizing the analysis that Hytrol employees use to justify the moving of parts to the punching machines. Now Jasia will discuss the results from our recommendations concerning the 5 candidate parts we did this analysis on.
Thank you, Alyssa. So we ran the 5 parts through our tool and got the expected net present value, expected return on investment, and expected payback period for each part. 3 of the parts, the ones in the middle with the stars by them, can be punched on the same die set, and we see that these parts have the shortest payback period and highest return on investments. The other 2 parts, the first and last parts on the table, do take a little longer to repay for themselves, but they will still be a good investment since they have high probabilities of success. Our final recommendations will be that Hytrol switches production for all 5 parts with an expected net present value of about $40,000. We do want to note that this $40,000 only accounts for the 5 parts that we ran through our tool and not the 65,000 parts that Hytrol manufactures. We do believe that if they run all of their parts through our tool, they will generate a great deal in savings. I will now pass it to Matt, who will conclude our presentation.
Thank you. So in conclusion, we started this semester with the goal of reducing Hytrol scrap and production costs. So we began by conducting a pre-analysis on scrap. This allowed us to discover that the laser and punching operations were the primary contributors of scrap. and that Hytrol has been moving the production of parts from the laser onto the punch because of the advantages it provides, which are the lower production times, the lower scrap production, and the lower operating costs. And so this finding is what motivated us to create a cost-benefit analysis tool to assist Hytrol decision makers in identifying the parts that are best suited for the punch to have the most impact on reducing their scrap and their production costs. So in order to do this, we derived a net present value equation that will estimate the financial impact of moving a part from the laser to the punch by using various cost parameters. We also incorporated a Monte Carlo simulation, which allows us to account for the uncertainty in some of these parameters. So we then created an Excel decision support tool that uses both of these features so that Hytrol can use this methodology anytime they want to determine which parts to move to the punch. And so finally, testing our tool on 5 parts that Hytrol gave us allowed us to identify $40,000 in potential savings across a 7-year time horizon. So we believe that if this tool is applied to any of Hytrol's 65,000 list of parts, the potential savings could be much higher. And they now have a much better ability to locate the parts that are financially best suited for the punch. So we will now hand it over to our industry partner, Ken Nickerson, who is an industrial engineering manager from Hytrol, to say a few words, and then we will allow for any questions.
Thank you, Matt. On behalf of Hytrol, I'd like to thank the team for all the work they did on this project this year. As you saw, they did a good job running some analysis to determine our biggest scrap contributor, and also given that contributor came up with a good tool for us to narrow down thousands and thousands of parts to find the best candidate to go from a laser to a punch. Not only that, gave us the ability to have that cost data together, so when we present this to our management and our decision makers, we would have the data behind that to make a good decision. So I think it's going to be a really good tool for us, and we appreciate the team's work on this, and thank you.
Thank you, Ken. So now we can open up for any questions that anyone has.